Okay, this session we continue cryptography and security with chapter 2, where we deal with the classical encryption technique. So we will start with the conventional encryption, which is the symmetric encryption model. And after that, we will investigate the substitution technique and the transposition technique, so the Rotor machine and the steganography. So let's start with the symmetric encryption. It's really the conventional encryption because we are using a single key encryption. It's at the transmitter and at the receiver. And it's really the most widely used type of encryption. So the classical system is as follows in a simplified form. So we have the plain text, which is the text before the encryption. And here we have a specific encryption algorithm. And in order to achieve the encryption, we are using a secret key, which is shared between the transmitter and the receiver. And after that, we have here the ciphertext, and ciphertext is sent to the receiver. At the receiver side, we have a decryption algorithm, and using the same secret key, it's possible to decrypt the ciphertext in order to have a plain text. So it's symmetric or one key encryption scheme because we are using the same key at the encryption and at the decryption. So we need to share this key between the sender and the receiver in a secure way. So this key should be shared between the transmitter and the receiver in a secure way. So this is the simplified model of symmetric encryption. If we want to go further in this part, so here we have the source where we have the plain text, we have the encryption algorithm, and here is the secret key. It's the same key as we said that should be shared between the transmitter and the receiver, and it's shared using a secure channel. And here at the reception, we have the decryption using the same key and in the plain text. However, when transmitting this ciphertext, here we have the ciphertext. We remember that we talk about cryptanalysis, and in this case, there is a possibility to try to analyze the ciphertext in order to find even the plain text or the key. So this is what we call cryptanalysis. It's a kind of analysis of the algorithm in order to know what could be the plain text or what could be the key. That's what we call cryptanalysis. So if we want to go in details, so as we said, cryptanalysis, it's a kind of attack that rely on the nature of the algorithm. Okay, in order to recover the plain text, so they try to exploit the characteristic of the algorithm to try to deduce a specific plain text. For example, if we have a specific plain text with zeros or with ones, or if you know that, for example, there is a specific pattern in the text, so they try to take into consideration the characteristic of the algorithm in order to deduce some plain text. Okay, but this is what we call the cryptanalysis. And we have another type of attack, which is the brute force attack. So the brute force attack is a kind of attack that try every possible key on a ciphertext in order to find the plain text. So here they consider that if we can try every possible key, so it's possible that we have a half of all possible key. The probability is to check, for example, half possible keys in order to recover. So it's in average. Okay. So this is what we call brute force attack. Assume that, for example, you have a secret key with the size, for example, 10 bits. Okay, it's a simple example. It's not very secure. So you have to try all possible values of those 10 bits, and one of them will be the key. So that's why we call it a brute force attack, because we try every possible key. Okay, but typically 10 bits it's not secure, so that's why we will see that we have a key size up to 256 or more, or 512 and so on. Okay. So what are the different type of attack on encrypted message? So here we we will see together what are the different types of attack. The first one is the ciphertext only. So in this case, the cryptanalyst that is trying to make this attack know the encryption algorithm and the ciphertext. So if the attacker is aware about the encryption algorithm used in this encryption process and is able to have the ciphertext, so he will try to make an attack, and this attack is called ciphertext only. Okay. Another one is what we call noun plain text. So in this case, the cryptanalyst know the encryption algorithm and know the ciphertext, and he, he is aware about one or more plain ciphertext pair formed with a secret key. So it was possible for this attacker to know some couple of plain ciphertext. So that's why we call it in this case chosen. Sorry, noun plain text. Okay, it could be any couple of plain ciphertext. Okay. The third type is the chosen ciphertext. Here, in this case, it's really a noun plain text. It's a noun plain text, but the plain message here are chosen by the cryptanalysis together with its corresponding ciphertext generated with the secret key. So with chosen plain text, it's a noun plain text, but the couple plain text ciphertext are chosen by the cryptanalysis, and typically they are chosen in a way that facilitate the attack, that accelerate the attack. Choosing ciphertext, here we have the encryption algorithm, we have the ciphertext, but we have a ciphertext chosen by the cryptanalysis together with its corresponding decrypted plain text. So here, according to the this kind of attack, it's possible to have a specific ciphertext pattern and it's plain text, and that's why we call it chosen ciphertext. The last one is the chosen text, and in this case, the attacker will have the encryption algorithm, the ciphertext, and also plain message chosen by cryptanalysis together with its corresponding ciphertext, and also the attacker will have a kind of ciphertext chosen by cryptanalysis together with its corresponding decrypted plain text. Uh, so that's why when we thought chosen text, it's really the chosen plain text in addition to the chosen cipher text. So those typically are the different type of attack on encrypted message. So typically now, if you read a paper or you want to know something, maybe they say that we have to test down plain text attack, or this algorithm or this scheme or this crypto system is robust against chosen plain text attack. So you are aware now what's each type means. Okay. So as we said in brute force attack, I already presented this. So here we should try every possible key, and in average we consider that half of all possible key must be tried to have an attack or to achieve the success of the attack. And generally to supplement the brute force approach, some degree of knowledge about the expected plain text is needed, and some mean of automatically distinguish plain text from garbage is also needed. Those are typically to, let's say, as a supplementary conditions for the brute force attack or the brute force approach. So after now after describing the different attack, let's see together how we evaluate the security of an encryption scheme. So we have two what we call conditions. We have what we call unconditionally secure, and here it's no matter how much time upon that, it's impossible for him or her to decrypt the ciphertext simply because the required information is not there. So typically, we could prove in theory that this scheme is unconditionally secure. So even if you have chosen ciphertext or any other, it's not possible to decrypt this ciphertext. That's what we call unconditionally secure. Another type of security, which is computationally secure, here we know that it's possible to attack the scheme, but the cost of breaking the cipher exceed the value of the encryption information or the encrypted information. So here, when we say that I want to send an information to, let's say, a destination, and at the destination they will decrypt this information and they will react according to this information. So in this case, if anyone could make an attack and decrypt this message, and this message will take a time such that the receiver will know the information, and when the receiver know the information, it's not, let's say, a problem that anyone could have this information. So in this case, if the time exceed the receiving time and the decryption time and the receiver, so in this case we can consider that it's computationally secure. يعني المعلومة بطلت مهمة بمجرد ما عرفها الريسيفر، بطلت المعلومة مهمة حتى لو عاد عمل لها decryption بعد ما كانت وصلت للريسيفر واستعملها. So it's not a problem in this case. That's what we call it computationally secure. Okay. So the time required to break the cipher exceed the useful lifetime of this information. This is to summarize the idea. So after having the different definition, let's start together now with the different technique. We start with the substitution technique. So typically in the substitution technique, we try to replace one of the letters is one in which the letters of plain text are replaced by other letters or by number or symbol. So for example, here we have a letter, we have a plain text. So the letters of the plain text are replaced by other letters or numbers or symbols. Okay, so in this case, if the plain text is viewed as a sequence of bits, so it's possible to make a substitution to replace plain text bit pattern with other cipher text bit pattern. So it's possible also to apply it at bit level or at bit sequence. The first substitution, the first, let's say, algorithm adopting substitution is Caesar. Caesar is the simplest and the earliest known use of a substitution cipher. It's used by Cesar, Julius Caesar, and it involves replacing each letter of the alphabet with the letter standing 3 places further down to the alphabet. So let's say, for example, here, the plain text is meet me after the toga party. So it's the plain text. Typically, we use the plain text just for representation for us to be a lowercase and lowercase letter, and the ciphertext, it will be the upper case letter. So here meet me after, so M is encrypted and it's substituted to be P, E, H, E, H, and so on. So Caesar is working as pawn, so it's a kind of shift, a place in alphabet, and typically by 3. So typically, if we shift 3 place, we reach P. If E, we shift 3 place, we reach H, and so on. Okay, so A, it will be B, C, and D. So that's why A is encrypted as D, and so on. Okay, so it's shifted 3 places. If we want to represent this, we can define that we have the alphabet, which is 26 letter, okay, and we give a number, a mathematical number of each of them. So we give A 0, B 1, and so on up to Z is 25. Okay. And if we want to express the Caesar algorithm using this, so we say that each letter is represented by a number, and after that we apply that the ciphertext equal the encryption of the plain text shifted by 3. Typically we say 3, or this is the key, which is a 3, and this is the plain text, and we obtain it's equal p plus 3 mod 26. Okay, so this is the way to work. So if you want to encrypt A, in this case the ciphertext of A, it will be A, which is 0, so 0 plus 3 mod 26 equal 3, which is in this case D. So the cipher of encryption of 3A equal D. Okay, if we want to encrypt M is 12, so it will be 12 plus 3 mod 26 equal 15, and 15 is P. Okay, so the encryption of M is P, and typically in this case we say that the cipher of 3M equal P, and so on. Okay, so it's possible to encrypt like this. So in order to decrypt, so that's the, we say that 3 is the key. So the receiver should be aware that the key, the secret key is 3. So in this case, it's possible to decrypt, and the decryption algorithm will be to have the plain text will equal the decryption of 3 ciphertext, which equal ciphertext minus the 3 mod 26, and we are able to recover the plain text. So Caesar algorithm proposed with a secret key equal 3, and it's possible to take k any value in the range of 1 to 25, and it's possible to use this. Okay, so to summarize, so we have the ciphertext in general when we are using substitution. So the ciphertext will equal the encryption of the plain text with the key, okay, and is equal P plus K mod 26. And if we want to decipher, so we obtain the plain text, and in this case the plain text is the decryption of the key, and we have the ciphertext, and it is equal to the ciphertext minus K mod 26, and we say that K is the secret key, could be any value from 1 to 25. So in this Caesar cipher, you can conclude that it's the brute force attack. It's not difficult because you can try all the 25 possible key. For example, assume that you intercept this ciphertext. Okay, this is the ciphertext, and you know that the algorithm, the used algorithm is Caesar algorithm. So in this case, you can try all possible keys. You can try k equal 1, and you apply c minus 1 mod 26. You can try 2, c minus 2 mod 26, c minus 3. Here, we tried all different key up to 25, and we try to see which text uh, is let's say a valid one, and we can conclude that this text is a valid text, and in this case we can make this brute force attack. And so in this case it's not very difficult in Caesar algorithm to make a brute force attack. Okay, but it's really uh, an oldest. It's the one of the first encryption algorithm, so it's not robust. But at that time, it was very useful. Okay, to send a message. So this is the example of encrypted text. For example, if we want to make substitution, and now let's see another cipher, which is monoalphabetic cipher. And here we will see together that we can use permutation. And if you want to use permutation, you know that if you have, let's say, a set of n element or s element, if you have n element, so in this case, if you want to make a permutation, so of those n elements, you have n factorial permutation. So that's why here it lies on the permutation, okay? And here it's one of the interesting approach to use monoalphabetic substitution cipher. And this approach could be applied per message, and we will see together. For example, here, for example, if you want to find the relative frequency, this is the alphabet. For example, this is one of the information used by the attacker in order to recover the ciphertext, because we are using an alphabet, okay? And in alphabet, we know that in certain language, for example, letter E is the relative frequency. So we can see each letter, the frequency of occurrence of each letter in the text. And we try to see how we can recover those information. This is a kind of attack with the cryptanalysis that take into consideration the nature of the language, the alphabet language. So in this case, for example, in the ciphertext, we try to find the letter with the highest frequency. In this case, we try to match it to E and to see if we can recover this text. If not, we can try other one, which is, for example, A or T or whatever. So this is a kind of uh, attack that take into consideration the relative frequency of the letter. Okay. So let's see together monoalphabetic cipher where we try to avoid the frequency data, because we said if you want to apply it, using one letter, so it's possible based on the relative frequency of letters in the alphabet to detect the plain text or to try to make an attack. So here the idea is to make multiple substitutes. So instead of having one substitute, so we try to make one multiple substitute. Maybe we can make two-letter combination or three-letter combination and so on. We will see together how we can couple or make substitution based on two-letter or based on three-letter. Okay, let's see an example of this using Playfair. Okay, uh, Playfair. So as we said, in Playfair, we are using multiple letter encryption. And as we said, the objective here to avoid the attack of monoalphabetic cipher, because it's possible, as we said, to find the relative frequency of letter when we compare it to, let's say, to the standard frequency distribution, for example, for any language. So that's why to avoid this, we try to encrypt multiple letter, okay? And here we try to avoid this kind of attack. So we treat the diagram. For example, in a play fair cipher, we are using two letter, okay? And this is based on the use of 5 times 5 matrix of letter. And this is the secret key. Okay, and it's invented. It's one of an old also algorithm, and it's used in the World War, the First World War, and also in the Second World War. And let's see together how it works. As we said, we have a secret key, and the objective here is to construct the keyword. So let's say we are using the secret key monarchy. This is the secret key. So the objective here is to try to build the 5 times 5 matrix. So we have to put a matrix 5 and 5. And we put monarchy. And after that, we should complete the alphabetic in the order. يعني من كفي alphabetic. A is already, so we should put B. After B, C. C is here, so D, E, F, G, K, L. M is already, so we skip it. P, Q, and then so on to have all letter. Because we have 26 letter and we have 25 places because we have a matrix 5 times 5. So typically I and J are considered only one letter. So it's possible to use I or J, and it's very easy in the plain text or in general in the plain text to know the word because we are working with letters. So it's very easy for in any language to conclude that it is I or J. Okay. So we build this secret key. So now how we can let's say encrypt. Okay, let's try to encrypt. Okay, how the encryption is done. Okay, so the idea here is to try to have, let's say, uh, a kind of pair of letters. So if you want to encrypt, you will not encrypt letter by letter, you encrypt each two letters together. Okay, so typically each pair of letter, how to say each pair, each, sorry, each, each pair of letter is typically replaced by the letter that lies in its row and the column occupied by the other letter. Okay, so typically uh, we take in its row and the column occupied by the other letter. For example, here if we can take an example, let's say I want to encrypt, for example, HS, for example, here HS. This is the plain text HS. Okay. How to encrypt HS? So typically, we should take, as we say, the row of the first letter, which is H here, and the colon of the second letter, which is S, and the letter here will be B. Okay, so H will be B, and for S we should have the row and the colon, it will be B. Okay, if we want to take for example NS, so for N here is N and S. Okay, if we want N, as we said, N as it will be A, and for S and N it will be Q, and so on. So here we deal uh, uh, with the encryption of two letters together. So we have some special cases where if, for example, the plain text letter are in the, let's say, same, uh, for example, let's take that example. We have two letters together. For example, meet. Here, if we have, let's say, or here, if we want to encrypt this, we have to take, as we said, a couple of two, but here we have 2L, and when we have the same pair, in this case, we should separate them by IX. So in this case, we have BA as a couple, LX as a couple, LR, and so on. Okay, so we have to put an X, and after that, when we, for example, it's okay, when we recover, it's possible to remove the X. So the objective of this X is to avoid that we have a pair of letter with the same letter. Okay. So here in this case, we should encrypt BALXLOON. Okay, so in this case, if to avoid that we have a pair of the same text. Okay. So another special case, if we have, for example, two plain text in the same row. For example, MO or MN, how we deal with it. So in this case, we shift to the right. Okay, in this case, we shift because we're in the same row. We shift to the right. Okay, so if we have, for example, M, N, M, N, because they are in the same row, we shift to the right a letter. So M will be O and N will be A. Okay. For example, if it's A, R, the plain text, A will be R, and R we shift to this direction, it will be RM. Okay. So this is the case if we have two letters in the same row. And the last case if we have, let's say, two plain text letter in the same column. So in this case, okay, we have to also shift, okay, and in this case we shift in order uh, for example, if we have M and U, in this case M will be C, M will be C, and U will be M. Okay, so we shift down one letter, and U will be on the top of the column. Oh, it's a circular shift. Okay, so is it clear for you? This will cover all cases in a Playfair cipher. Okay, so as we said, in this case, it's better than monoalphabetic. Why? Because we are using two letters, so we have 26 times 26 possible diagram with possible two letter. Okay, and uh, it's better than cipher in the monoalphabetic, but you know that it's possible also to use, let's say, relative frequency, but in this case, instead of using relative frequency of one letter, to try to use relative frequencies of two letters. uh, uh, it's possible to break it. Okay, it's not very difficult to break it, because we can have in any language a relative frequency of two letters together. For example, in English, the it's well used, for example, or me, or whatever. Okay, so this is an interesting uh, cipher, an interesting symmetric cipher based on letter, which is well known. And here, if you want to compare, this is the plain text, okay, and this is the Playfair. So the relative frequency, it's also possible to use this normalized relative frequency in this case. Okay. Uh, Other cipher algorithm, which is uh, uh, Hill cipher. It's also an advanced or better than the previous one, better than César, better than Playfair, and it's developed in 1929, and it tried to completely hide the single letter frequencies. So the objective here, as we said, that if we can use the relative frequency of letters or even of two letters, so it's possible to break the algorithm. So Hill tried to do in another way and to hide this single letter frequency. So the use of a large matrix hide more frequencies information. So the idea here was to have what we call multi-letter cipher. And in this multi-letter cipher, Hill used a matrix. Example, we will see the Hill cipher using the 3 times 3 Hill cipher, okay, which hides not only the single letter but also two letters frequency information. As we said in Playfair, we have two letters, so it's possible with this algorithm to hide this. It's really strong against ciphertext only attack, but it's broken with non-plain text. If we know any, as we remember, any plain text is possible to recover it. How it works, I will give you how. Uh, so we should have a kind of matrix, okay, and using this matrix, which will be the secret key. So typically we have, let's say we have a secret key, which is the matrix, and in this case, it will be, this is the key, which is K11, K12, K13, K21, K22, K23, K31, K32, K33. So typically, if we want to cipher any text, in this case, the cipher typically is used as follows. We say that the cipher text is, let's say, here we cipher H3 letter together. So this is the C1, C2, C3 will equal plain text P1, P2, P3 times the matrix K. Okay, that's the typical way, and because we are working in alphabetic, so it's mod 26. Okay, so in general, it will be like this. So the ciphertext C1 will equal uh, K11 P1 Z plus K21 here, K21 P2 plus K31 P3 mod 26. If I want to find C2, C2 is equal P11 or K12 P1 plus K22 P2 plus K32 P3 mod 26. And if I want to recover C3, I want to encrypt and find C3, it will be K. So it will be K13 P1 plus K 23 P2 plus K31 P3. Sorry, K33. It's this one, K33 P3. K1323 mod 26. Okay. In order to recover, we should, as we said, we should find for every secret key K minus 1, which is the inverse matrix, and as we said, it should be the inverse matrix mod 26. Okay. It's well-known idea, so you should find key times key minus 1, t times key minus 1 mod 26 typically should equal 111000000. Okay, so this is the typically how to find the inverse of the key, which should be k minus 1. Okay, and typically it's done like this, and we are working mode 26. Okay, so the decryption in this case, how the decryption is done? The decryption is done as we said using k minus 1. Okay, so typically, if I want to summarize, we said that the cipher matrix vector here C equal a plain text times k mod 26. If I want to find the plain text to decrypt, so typically it will be the cipher text k minus 1 mod 26. So the cipher text is pk and it will be pk k minus 1 and it will be okay. Okay, so this is HAL cipher. As we said, with polyalphabetic substitution cipher, it improved in comparison to the monoalphabetic technique. It's improved because we are using different monoalphabetic substitution, and the key is typically used in a particular rule is chosen for a given transformation. As we said, for example, in play cipher. Okay, we used the key monarchy, and after that we build the 5 times type matrix. In Hill cipher, we are using 3 times 3 key matrix. It will be also possible to have uh, uh, another matrix 4 times 4 or 5 times 5 and so on. Now with polyalphabetic, we have multiple ciphertext alphabetic, okay, and we have a set of, let's say, monoalphabetic substitution rule. We are using them. And we can see, for example, Vigenère cipher. Okay, it's a kind of polyalphabetic substitution cipher. And in this scheme, we have substitution rules that consist of 26 Caesar cipher with shifts of 0 through 27. So it's like a system where each, let's say, we apply Caesar, but it's Caesar is applied with a different key on different letters. So we are not using the same key for all letters. For each letter, we have another key. So in this case, each cipher is denoted by a key letter, which is the ciphertext letter that substitutes for the plain text. If I want to put it, so typically for each cipher letter, it will be the plain, as we said, the key, the plain, pi plus ki k mod 26. So we have a key for each letter. So if you, let's say, we have a kind of sequence of letter of plain text letter, okay, and the key will consist the sequence of letter. For example, typically if we have the plain text, for example, P0, P1, P2, enter P, let's say, for example, N, and typically it should be less than 26 to be efficient, okay? So typically for each plain text, we should have key. The key in this case will be K0, K1, K2 until Kn. Okay, and we will apply the ciphertext in this case will be for each one, it will be different. So for C1, as we said, Ci equal Pi plus Ki. So here the frequency information cannot be recovered. Okay, cannot be recovered. Okay, so this is an example. This is an example. When I say the key K0, K1, K2, K3, and for the plain text, we will see an example. Here is an example. So to encrypt a message, a key is needed that's as long as the message. Usually the key is repeated because as we said here, the key maximum could be let's say 26, but if it's less than, we can repeat it And for example, let's consider that we want to encrypt the message we are discovered, save yourself, and the key, secret key is deceptive. So in this case, we should put the plain text, okay, and we should make deceptive, deceptive, deceptive. So the secret key will be D, E, the secret key will be E, A, the secret key will be C, R, the secret key will be E, and so on. And remember that using Caesar, we adopted for each letter a number, and D, it was 3, okay? So W, it will be Z, and so on, okay? So typically, this is how the general cipher is applied, and it's a kind of polyalphabetic cipher. As we said, it's a kind of multiple ciphertext alphabetic. Okay, we apply monoalphabetic rule at each letter. Okay, so in order to recover, we need this one, and we should we have the ciphertext, and we apply deceptive, 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 and here Z, it will be, here it was +3, here it will be -3 mod 26, and so on. Okay, so this is the deciphering. As we said, we have the plain text, the ciphertext, and the how to recover. Even this scheme is vulnerable to cryptanalysis because the key and the plain text share the same frequency distribution of letter. It's possible here to have a statistical technique because we are working on letters. Because we are working on letters, it's possible in this case to recover them. Okay, uh, and so on. It's possible also here to let's say to concatenate the keyword with the plain text, like here, for example. It's possible to do it, for example. Another scheme, which is Vernam. Vernam, it's also a kind of cipher, but it works at binary data. Here we work at binary data. So we have the plain text, okay, but it's not as letter, okay, it's a binary data. So in this case, the plain text is binary, so it's here a bit sequence, okay, and we have a key stream generator, and we obtain the ciphertext. So the key stream in this case, it's also a binary. And Vernam cipher, it's really a good cipher. It's a good cipher, but you should have a long key, okay? Because when you have a long key, it's possible when it's the key, it's not long, as we said. If it's, for example, 5 bits or 9 bits, it's very easy to break it. But when we have a long bit, or the bit is enough, it's possible in this case to avoid an attack. So Vernam cipher, it's an efficient algorithm with long key, okay, with long key. And another scheme, another ciphering scheme, which is one-time pad. So in this one-time pad is really an improvement of Vernam cipher. And the objective here is to use a random key. And this random key is as long as the message, so that the key need not to be repeated. Because you are not repeat the key, this means that you are using, let's say, a robust key, and the key is used to encrypt and decrypt a single message. So the key is used only once. So you are using it only once. You encrypt and you decrypt, and each new message require here a new key of the same length for the new message. And this is one of the robust scheme because it's unbreakable, because you produce output, random output, and there is no statistical relationship with the plain text. And for each message, you generate a new key, and this key is long as the text, as the plain text, and that's why it's really a robust scheme because the ciphertext contain no information whatsoever about the plain text. Okay, so no way to break this code. Uh, so as we said, the security here is really achieved or done due to the randomness of the key, because we say we have random key. Okay. So the question here in practice, how to try to have an efficient scheme in order to implement it. So there is different way to implement it in order to produce at each time a secret key that is not easy to guess or to make a statistical relation with the different one. Okay. So it's used in several application one time path. It's for example a kind of example, but it's not exactly the same. But just to have the idea is what we call the verification code. It's like one time secret key. You are using it only once. Okay, this is a kind of example. So at each time you generate another code. Okay. So as we said, the difficulty here, the one-time pad offer complete security, but in practice it has too difficult. So there is practical problem of making a large quantity of random key. You need a scheme in order to have this large quantity, and it should be done in a random, so to avoid any relationship between them. And the other thing is that for every message to be sent, you should have a key of equal length. So to send the message of length, for example, L, you should send a secret key in a secure way in order to encrypt. So how to send the key, how to share the key. This is also the key distribution problem, how to distribute the secret key in this scheme. So that's why, as we said, it's used in, let's say, in a small or in a specific application where you don't need to send a lot of message. You can use it only once or something like this. Because of this difficulty, the one pad is of limited utility is used really for low bandwidth channel that require very high security, and it's considered as a perfect secrecy because we are using the key only once. Okay. So it's typically used in application when you want to share only, let's say, one message, and after that you can move to another system. Okay. So after presenting the different substitution scheme, let's see together the transposition technique. In transposition technique, which is also an efficient mechanism, we perform some sort of permutation on the plain text layer letters, and here it's let's say it's a kind of sample cipher, but permutation is done in an efficient way to avoid, let's say, the attack. Let's see, take the example of railfan cipher. Here we consider that the plain text is written down as a sequence of diagonal and then read off as a sequence of row. For example, if you remember Meet Me after the Toga party, here we take the def of 2 and we write them like this: Meet me after and so on. And then we send the message like this. This part will be here and the second part will be there. And here is the encrypted message. If you want to do it, let's say with def3, it will be like this: meet me after and so on. So here we apply the real fans cipher with def equal 3 and so on. And after that, the cipher text will be this part followed by this part and followed by this part. So this is also an efficient, let's say, uh, uh, an efficient mechanism. It's another way to do transposition cipher here is to write the message in a rectangle, for example, row by row, and to read the message off. For example, if we have a message, for example, attack postponed here, we have a kind of secret key. This is the secret key, and in this secret key, we should write, because it's a length of 5, so we should write the message as 5 letters, and after that we go so attack postponed and tell who, for example. This is written like this, and the ciphertext will be, first we start by the first column, 1 T T N A, TTNA. Then the second is A, B, T, M, and so on. Okay. The third one is T, S, U, O, and so on. So in order to recover, it's just we need this 4, 3, 1, 2, 5, 6, 7. Okay. And I have this text. I should divide it over 7, and having every part. So here, when we divide to 7, we have 4, and I should put it like this, each 4 together. And T, T, and A, I will put them here, T, T, and A. The second is A, B, T, M, and so on. So I will recover the ciphertext. And typically, let's say if here the plain text is not multiple of 7, for example, we can add some pad at the end in order to have the multiple. Okay. So this is what we call row transposition cipher. It's also one of the efficient. It's let's say it's more secure than uh, than railfan cipher, because here we are using let's say a kind of transposition. It's more complex than the one than rail cipher. Okay, and so on. So this is an example of transposition technique. One important scheme with the rotor machine, and here the rotor machine is one of the machine used during the war and before. The objective here is to create a kind of multiple stage of encryption using rotors, and the objective here to have the substitution and the transposition. Okay, and as I said, because you have rotor, so you have the input, you have the defined output. So this is the 3 rotors and so on. So you have here at the output of this, you have some motion that achieve according to a predefined form the different substitution and the transposition. I will not go into details, but the idea here is that those rotors will achieve substitution and transposition. And here this is the initial setting, and after one keystroke we can see how it works. At the receiver we have the reverse according to the key. It's the same machine, we are able to recover the information. It's really an important let's say system used because it's based on cylinder. Okay, and we have multiple stage and multiple cylinder, and in each case here we have 26 letter, and here we have 26 letter, and here we have 26 letters. So we have 26 times 26 times 26, which is around we can multiply them, and this is we could be different substitution. Okay, and we apply this at each time and so on. So it's really an important at that time it was an important tool, and uh, they leads to create the DES we will see in the next chapter. So the rotor machine, it's also interesting machine. And finally, we want to talk about steganography. And in steganography here, the 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 sender will try to include the text in a message like this, and uh, the it's not possible without the secret key to know the message. Let's say I send you this text. Okay, you will find it's a normal text. Okay, يعني ما حدا بيشك إنه هذا it's a simple letter. But if I want to say you that the secret key is to use for example, the first letters of each word of the overall message. Okay, okay, if you want to take, for example, uh, uh, the first letter, okay, of each. We should specify something, okay, to say that, let's say the first letter here, a greeting to all at Export. Okay, here many thanks for your letter. Okay, we have to specify a kind of secret key to say, for example, as I say, first letter of each word. Okay, this could be a secret key, and you try to extract those information, and when you extract them, you can have the message. So I will let you try to discover in this letter what could be the secret message. Sorry, what could be the encrypted text? Because it's inserted here, okay, within this text, okay. But if you want to make an attack, let's say you want to make an attack, you will try to find the secret key, for example, the last letter of each row of each line, the first letter of each line, the first letter of each row, and something like this. So uh, uh, it's possible to break it, but it's time consuming. It's time consuming, so it needs a time in order to find it. Okay. So maybe I will let you check what could be the message inserted in this text. Okay, so it's clear for you the steganography. زي مثل ما قلنا the message is really inside this text is hide in a way that it's considered as a simple message, okay? But when having the secret key, which is the way how it's inserted, we are able to recover the useful information, okay? هخليكم تشوفوا انتوا تطلعوا لي التكست من هيدا المسج من هيدا التكست، okay? Encrypted text, okay? So this is the text إذا ما كانت واضحة هون, you can check on this one, okay? And let me know what's the inserted text. Okay. So in this case, another technique of steganography, we can, for example, make a character marking to select letter of printed or type printing text over writing in pencil. هودي مثلا مثل الحبر السري or something like this, or invisible ink, a number of substances that can be used for writing but leave not visible. Pin puncture, small pin puncture on selected letter are ordinarily not visible unless the paper is held up in front of a light. Those are different type of steganography. Okay, or for example, typewriter correction used between line type with a black trident. The result of typing with the correction tape are visible only under the strong light. Something like this. هذي كلهم بيسموهم steganography. So to summarize in this chapter, we presented the different symmetric cipher model based on letter, وحكينا عن الكريبتو عن الكريبت analysis brute force attack, وشفنا substitution techniques سيزار mono alphabetic بريفير هيل البولي والوان تامبايد. حكينا عن transposition technique وبريفلي speaking عن الروتور ماشين وستيجانوغرافي. ففي مجموعة اكزرسيس لهيدا التشابتر لازم تشتغلوهم. اوكي، وهبلش بالشابتر اللي وراه اللي هو الداتا انكريبشن ستاندرد. إذا في أي أسئلة أو أي شيء please send me a message in order to check it online. إن شاء الله بلكي ابتداء من الأسبوع الجاي بنبلش نطلع أونلاين. أوكي، يلا يعطيكم العافية.